Good morning. I shall continue again the discussion where I left in my last class. I got a feedback that the diagram which was drawn was not that visible, and intentionally I have drawn it again, and I hope this diagram is more visible to you. I just go back and explain this governor, and this governor is what I call it as a quarter governor. This line represents the spindle of the governor. I have drawn only half of the governor, and I know that the other half is going to be symmetric, and exactly the other side we have this. So there is a collar to which the upper arm is fixed. Please remember, this collar is rigidly attached to the shaft. So whatever the speed of the shaft, and the same is the speed of this collar also. So you have upper arm, and then you have lower arm which is attached to the sleeve. This is half of the sleeve what I have shown, and the lower end of the lower arm is attached to the sleeve, and both the ends, one end of upper arm and one end of the lower arm, they are connected by means of a turning pair, and at the same position you have what is called as governor ball. You have exactly the same thing this side. Okay, some of the terms. So RCU, the radius of the collar at the upper end, this, and the length of the upper arm, this is what I call as LU, and the length of the lower arm, BC, and this is what I call it as half of the sleeve, whatever I have shown. So that I call it as radius of the collar at the lower end. Then the ball at which it is revolving, the plane. Okay, this is the plane of rotation of the balls. And the distance between the center of the ball and the axis of the spindle is what I call it as the radius of rotation of the balls. So these values, this is what. So simultaneously I also would like to explain you that how we can solve a problem in general without any values. So I expect you all write the given value when you are solving a problem in terms of meters, and you write it down. And n is in RPM, it may be given or it may be asked, and the relationship between n and omega. So as you all know, this is how it is represented. Then you also have two angles, what are called as alpha and beta. Alpha is the angle made by the upper arm with the spindle axis. Similarly, beta is the angle made by the lower arm with the spindle axis. So if the length of the upper arm and lower arm and RCU and RCL, if they are equal, in that case alpha is going to be equal to beta. But I would like to make this analysis as general as possible, so that I assume that all of them are different. But when you start solving a problem, sometimes or many times they may happen that LU is equal to L, RCU is equal to RCL, etc. In that case alpha is going to be equal to beta. Don't worry about it. So in addition to this, you also have something what is called as the EMP, the mass of each ball, and what is called as the mass of sleeve, and all these, both of these are supposed to be in terms of kg. Okay, this is what, and whatever the analysis, this is what I am calling as analysis of outer governor without friction. So I am not considering friction right now, and if I don't take it into account, then how analysis is to be carried out. That's what I want to demonstrate. So along with this, I also have shown the various forces that are going to act. Okay, in this case, so you have a force what is called a centrifugal force, which is equal to mv omega square r. Then you have weight of the ball that is acting vertically downwards, that is equal to mv into g. Then you have the sleeve. The sleeve is of mass ms, and the weight of the sleeve is ms into g, and that is imagined to be acting at the axis. And this I want to dissolve it into two parts, say one component here and other component here, and which I can imagine that at these two components are equal, and that is equal to ms into g divided by 2. So this is the sleeve force, weight. This is the weight of the ball, and this is the centrifugal force. So these three forces are acting, and under these three forces, these balls are revolving at a constant radius r, and therefore this these balls with respect to the horizontal movement in the plane of rotation, so it is constant, that is it is fixed, that fixed in the sense it is not changing, this R value is not changing, and therefore I can say that it is in the equilibrium state, and therefore I would like to apply equilibrium condition. So for doing that, I am just made few small construction here, and I take moment about point I, Fc multiplied by Bd is equal to Ms into G divided by 2 multiplied by Ci plus Mv into G multiplied by Di. This is what I write down. This is what is the moment equation, and I further simplify and all that, and this is the equation which I have shown you in the last class. Omega square is equal to G upon H. So this is equal to Mv plus Ms by 2 into 1 plus K upon Mv. So H is in the term what is called as the height of the governor. So what is the height of the governor? You can return, okay, which is not going to be measured, it has to be calculated. So as per the definition of the height of a governor, there is nothing but the distance of the intersection of the upper arm with the spindle axis. That is nothing but this point. You have upper arm here, you extend it till it intersects, and this is the point. The distance of this point from this, what is this? This is the plane of rotation of the balls. The distance of intersection of upper arm with the spindle axis from the plane of rotation is what is called as H. That is height of the governor. So this is how what we have got the relations between omega and H and Mv, Ms, etc. etc. And usually, though I don't intend you to use this ready-made expression and every problem, numerical problem, you can analyze in this way, etc. But even if you use it as if it is a ready-made formula, please remember this is the ready-made formula for this figure. Please remember this and also remember this diagram. Then, whenever you solve, usually some data, okay, data is given related to this, some information is given, and usually one of them is unknown, and that's what you normally ask. Okay, so omega normally, let me assume that omega is unknown. Then I would like to find out G. Then G is known, that is the acceleration due to gravity. H is the height of the governor. So let me postpone it. So I shall find out what is called as alpha. I would like to find out alpha. So go back to this diagram and make use of this triangle. So you can make use of this triangle. Okay, if I write down an expression of sine alpha is equal to this value. And what is this value? That is nothing but this value, that is the radius of rotation, minus this value, that is nothing but RCU. So sine alpha is equal to R minus RCU divided by LU. This will give you what is sine alpha. So knowing these values, you can find out sine alpha, and from that you can find out easily what is the value of alpha. Similarly, sine beta. So beta, if I want to find out, then I can easily make use of this sine beta is equal to sine beta. Again, make use of this triangle. That is nothing but this value. The opposite side, that is nothing but R minus RCL. R minus RCL divided by LL will give you what is sine beta, and from that you can easily find out beta. Make use of this alpha and beta and find out what is K, which is nothing but tan beta divided by tan alpha. So if you do that, K can be found out. And knowing the value of alpha, so now I want to find out what is H. How to find out H? H can be found out very easily. Okay, so if I take this, so I can this is alpha. You know that this line and this line they are parallel, and therefore this angle is also alpha. And therefore, so if I write down what is the tan alpha, I shall write down the expression of tan alpha. So I know, remember, I know already alpha. Therefore, tan alpha is equal to opposite side. That is nothing but this R divided by adjacent side. That is nothing but this. This value is what is H. So tan alpha is equal to R by H, and knowing the value of alpha, you can easily find out H. and therefore we can substitute all the nodes G, H, M, E, M, S and M, P and K, and that is how you can find out what is called as the equilibrium speed of the governor. So what do I mean by equilibrium speed? Because I presume that the load on the governor, the load on the engine is constant, and therefore engine is running at a constant speed, and the governor engine shaft is connected to the spindle of the governor, and therefore the governor spindle also is running at a constant speed, and therefore what is that speed? That speed I call it as equilibrium speed. Please remember, so this is what I find out the omega, this is what I call it as the equilibrium speed of the governor for this radius or for this position of the sleeve. Remember, as the load on the engine changes, its speed changes, and the speed of this governor spindle also changes, and as the speed changes, these balls, so here the centrifugal force will change. Then accordingly, if it is more, then the ball will move out. If the ball moves out, remember this end cannot move at all, this end is fixed. When this moves, then automatically the sleeve has to be lifted up, the sleeve has to go up. And similarly, if the speed comes down, the balls come inwards, the sleeve comes downwards. Okay, so depending upon, so now whatever the diagram I have shown now, I shall presume that the sleeve is not in the lowest position or sleeve is not in the topmost position. Okay, you have certain limits. The sleeve cannot go beyond certain below the lowest position. As I say, this goes down in, as the speed becomes lesser and lesser. So this ball goes inside and the sleeve comes downwards. There is a limit for that position, and that position, the lowest position of the sleeve, I call it the lowest position of the sleeve, and at that time the speed is going to be the lowest. Let me call that lowest position as lowest speed as say omega 1. At that time the sleeve is at its bottommost position. And similarly, when the sleeve goes, when the speed increases, the balls move outwards, and then the sleeve goes on moving, and it reaches the topmost position, and beyond which the sleeve is not allowed to move up or inwards. That I say that the maximum position, and that speed I call it as omega 2. So omega 1 is the lowest speed, and omega 2 is the highest speed. And usually this omega 2 minus omega 1 is called as range of speed. And whatever the range of speed that I find out in this way, and this is called as without considering friction. Without considering friction, what is the range of speed of the governor, and that's what you find out what omega 2 and omega 1. So please remember here, when the sleeve position is different, say at its lowest position, though these values RCU, LU, LL, RCL, they don't change. So whether the sleeve is at the bottommost position or the topmost position, these values remain same. But some of the values they change. The value of R will change. Okay? So those values I call them as, say, for the lowest position. For the lowest position, I have what is called as alpha 1, I have what is called as beta 1, I have what is called as R1. Okay, these are the changes, and therefore, so alpha 1, beta 1, R1, these are the values, and for that, so again you find out, so sin alpha 1, sin beta 1, and then K1, then what is H1, then that is how you find out what is called as omega 1. Similarly, when the sleeve moves to the topmost position, that time I have what is called as alpha 2, beta 2, and R2. Alpha 2, beta 2 and R2, and using this to find out what is the speed, and that speed is the topmost speed, the speed at the top corresponding to the topmost position of the sleeve, which we also call it as the highest speed of the governor. Okay, so now you can use this alpha 1, beta 1, R1, alpha 2, beta 2, R2 in general corresponding to the lowest position, corresponding to the topmost position. And if you are talking in between, and I simply call it as alpha, beta, K, and okay, and what is called as omega. And one more thing which may be asked, what is the sleeve movement between the lowest position and the topmost position? For example, so right now, as I said, this diagram corresponds to a position of the sleeve in between. Say it is not in the lowest position, it is not in the topmost position. When the sleeve goes to the topmost position, let me assume, say it is somewhere here, this is the lowest position. And similarly, so when the speed increases, sleeve goes beyond this, and let me assume that this is the topmost position. This movement is what is called as the sleeve displacement or sleeve movement. So how to find this position? How to find out this? If you want to know what is the sleeve displacement corresponding to the bottommost position and lowest speed and corresponding to highest speed, how much sleeve is going to move if you want to calculate it. Okay, so sleeve is at the bottommost position. Please remember this distance, this point is fixed. So I would like to measure the distance from here to here, and then I also measure this distance. So difference between this distance minus this distance will give you what is the sleeve movement. So therefore sleeve movement or sleeve displacement, this is also called as sleeve displacement, is equal to, so I would like to know from here up to the lowest position. So what is this distance? This is same as this value, that is, this is nothing but LU cos alpha. So LU cos, so corresponding to this position, it is lowest position, the angle, that angle I call it as alpha 1. LU cos alpha 1, that is this, and that time this is here, and this distance is nothing but LL cos beta plus LL cos beta 1. This distance will give you what is the position of the sleeve from the upper fixed end of the column. So minus similar distance LU cos corresponding to the topmost position cos alpha 2 plus LL cos beta 2. This will tell you what is this distance. If you calculate this will tell you what is the sleeve displacement. Okay, so I hope you will be able to solve your problem based on this, using this, how much is the sleeve movement, etc. And maybe in my next class, it is more of repetition of what I did here in my previous class, but I hope now everything is clear. Okay, and what will be the effect of friction, that I am going to discuss in my next class. So you all know that if anyone, okay, who doesn't bother about all the effects on him, then we normally call him as insensitive person. Okay, so he is not responding to anything. A similar thing we have here also. So if I have friction, then governor to at any position it becomes insensitive for a certain range of speed. Okay, and that's what we call it as the governor becomes insensitive for when I take friction into account, and how is that, how much is that, etc. That I shall discuss in my next class. Okay, thank you.